Welcome to the final installment of your Monte Carlo Simulation and Modeling series. In the previous segment, we looked into the concept of Monte Carlo Simulation, which involves the random generation of data within defined scenario boundaries, following one or a combination of several probability distributions. This approach allows us to mimic potential future outcomes, enabling us to apply descriptive statistics and gain insights into the range and likelihood of various results. In this video, we will build upon that by exploring how to utilize Microsoft Excel for generating data that follows normal and beta distributions. Additionally, we will walk through the general steps in modeling and look at a more comprehensive example to illustrate the process. The first item on the agenda should be fairly simple. Remember from the last video that we used the inverse binomial function to turn uniformly distributed random values ranging from 0 to 1 into binomially distributed integers ranging from 0 to the upper possible limit. Using that exact same logic, we can utilize the inverse normal distribution to generate normally distributed data, and we can use the inverse beta distribution to generate beta distributed data. Let's see that in action. First, I define that I want a normal distribution with a mean of 10 and a standard deviation of 2. Next, I'm generating some row numbering to get me 10,000 iterations. I am utilizing the function norminf because I want to simulate normally distributed data. Instead of providing a fixed quantile, I use rand to generate random values between 0 and 1, followed by the predefined mean and the standard deviation. I spread that formula across all rows. For analysis, let's find out the smallest value, the 0.025 quantile, the mean, the 0.975 quantile, and the largest value. The mean, as defined, is around 10. Also, for every normal distribution, 95% of the data should roughly be within a ±2 times sigma range around the mean. Here, that is 10 minus 4 equals 6 and 10 plus 4 equals 14. Let's also take a look at the distribution. Other than for the binomial distribution, which has discrete values, the normal distribution is continuous. Therefore, I need to define class boundaries. I'm using increments of 1, and instead of COUNTIF, I need to use an array function, which is frequency. And we find that our data looks normally distributed. Pretty much the same thing for beta distributed data. I actually can just reuse this sheet. For a beta distribution, we need alpha and beta as parameters. Let's take 4 and 8. And all I need to do now is go into the function and swap norm for beta. The rest stays exactly the same. Randomly generated probability, alpha and beta get picked up from the predefined cells, and that's it. The beta distribution is the probability of probabilities, so we should get values between 0 and 1. The descriptive parameters suggest a distribution that is skewed to the left, as it should be given our choice of alpha and beta. To inspect the distribution in more detail, let's use increments of 0.05. If I swap alpha and beta, as expected the distribution gets skewed to the right. And for larger alphas and betas, maybe 80 and 40, we get a much nearer and pointier distribution. So we have a fairly simple way of generating random data following predefined distributions. And basically, we can use that approach with whatever distribution we find most suitable in a given situation. Which brings us to the next point, the general steps in modeling. Number 1, we need to determine the variables that are most relevant to the problem at hand. Number 2, for each variable, we need to decide the distribution that best characterizes its realizations and the distribution's parameters. Number 3, we also need to specify the functional relationship between the variables. This basically gives us the model of which we, number 4, generate a large number of iterations. And number 5, we ultimately need to analyze the outcome. Let's follow these steps through with an example. Imagine you're managing a lodge accommodating groups of 25 tourists. At a certain point during their stay, you offer a boat tour, and you want to enhance your understanding of how many of your guests might be interested in joining, and how much non-alcoholic and alcoholic beverages you should have prepared for the excursion. Let's establish the variables we need to consider. But before we start, please note that everything we are about to define in this section is a matter of interpretation. I suppose you will find my choices understandable. However, someone else might take a different approach, which might be equally valid. Now let's start. First, we'll determine the number of participants for the boat tour. This is directly relevant and also serves as an input for estimating beverage consumption. Secondly, there will be individuals who abstain from alcohol entirely, while others might opt for a mix of alcoholic and non-alcoholic beverages. Next, we require estimates for the per-person consumption of non-alcoholic beverages by non-drinkers and those who choose a mix of drinks. Why differentiate between the two? Simply because we expect a noticeable difference between these groups, as the latter will have some of their beverages containing alcohol, which introduces another variable we must account for. From that, we will be able to calculate the total consumption of non-alcoholic and alcoholic drinks. Step number 2, we need to define distributions and distribution parameters. Here I have inserted a copy from step 1 with the defined variables carried over as headlines. Again, I will provide my assessment of what distribution reflects each variable best. Someone else might come to a different conclusion. Starting with the number of tour participants. Each guest might have a certain probability of being interested in partaking, and each round we have 25 persons to decide yes or no. Consequently, this may be well represented using a binomial distribution. However, I'm not perfectly certain about their participation probability, so I will randomly generate theta using a beta distribution. To determine the number of non-drinkers and mixed drinkers, I'll simulate a percentage of non-drinkers, again using a beta distribution. Subsequently, the counts for non-drinkers and mixed drinkers can be derived by a simple multiplication. The per-person consumption of non-alcoholic and alcoholic drinks is maybe the result of a multitude of factors, fluctuating around some average values. Therefore, it probably makes sense modeling them as normally distributed. Moving on to the parameters. The maximum number of participants is 25, and we may have the knowledge that from a total of 100, previously 74 have participated and 26 have not. This translates into an alpha of 75 and a beta of 27, if you want to use the beta distribution to inject theta. What proportion of participants will drink no alcohol? Unfortunately, we have not properly kept track of that, but let's say our best guess is a gut feel of a 4 to 8 parameter ratio. I put that in, but take a mental note to better pay attention to this in the future to improve our model. The normal distributions for the per-person consumptions require estimates for mu and sigma. Here I am providing some estimates in milliliters, which we either might get from analyzing previous tours, or if we do not have such data, they might be pure judgments. Let's code the functions. For the number of participants, I use binom inf. 25 guests, each being a trial who may or may not want to participate. The probability parameter we want to estimate via the beta function, so I put beta inf with the probability being random, and alpha and beta being 75 and 27 respectively. The last input is the quantile for binom inf, which we also want to generate at random. And we're done with the number of guests variable. Next, I want to simulate the percentage of non-drinkers using a beta distribution, with a random probability and alpha and beta being 4 and 8. The total number of non-drinkers and mixed drinkers follows from that, so we can look at that in a minute. The per person consumptions will be simulated using norm_inf with a random probability. And when I am fixing my parameter references to just the rows but not the columns, I can simply drag the formula across the 3 cells and they will pick up their respective parameters automatically. And then I am done, because the rest will follow in the next step, which is the specification of the functional relationship between the variables. The number of non-drinkers is the number of participants times the proportion of non-drinkers. I will round that to a whole number. If this was just an intermediate result, I could also leave decimal points. The difference between all participants and non-drinkers gives me the number of mixed drinkers. We do have the per person consumptions, so multiplying the number of non-drinkers with their per person consumption and adding the number of mixed drinkers times their per person consumption, I get the total consumption of non-alcoholic beverages. The total of alcoholic drinks results from the number of mixed drinkers times their per person consumption of alcoholic drinks. Finally, I will generate a large number of iterations of that calculation and analyze the outcome. So let's do maybe 100,000 iterations. And I am ready to analyze. Just as examples, I've created a distribution chart of the number of non-drinking and mixed drinking participants, and the distribution of total consumption of non-alcoholic and alcoholic beverages, which enables us to see the bulk of possibilities. Mostly, however, I would look at quantiles, such as the 5 and 95% quantiles, because they tell us the range of possibilities we would be faced with in a vast majority of cases. Lastly, a word of caution. What we are examining here is naturally not the truth. Any inaccuracies, errors or oversights we may have made in our assumptions regarding variables, distributions and parameters, or functional relationships will be carried forward to the results. Keep this in mind and scrutinize your inputs and outputs rigorously. For instance, you could experiment with altering certain parameters to observe how this influences the overall outcome. This is known as sensitivity analysis. You may discover that even a big change does not affect the outcome all too much. In such instances, you can relax. A rough estimate is good enough. However, when you notice that a minor change has a substantial impact, you need to exercise extra caution. Naturally, you might now wonder, what is big? What is small? I cannot provide a universal answer, as this depends on a specific context. For instance, if you receive a pay increase of €1 per hour, this is nice, but it won't revolutionize your life. Conversely, if you produce frozen pizza and for some reason your costs increase by €1 per piece, you could be facing significant challenges because profit margins in the frozen pizza industry are typically thin. As some general advice, however, I would like to say, the larger an element's impact is in relation to its changes, the more attention you need to pay in studying and designing that element, and the more accurate you need to be in measuring its inputs. And probably a key insight you will experience yourself when applying modeling techniques is that they never offer definitive answers. Their true value lies in giving you a deeper understanding of the problem and highlighting areas where further information and comprehension are needed. However, at this point, you should be able to break down more complex systems into their components and follow the general steps in modeling to simulate and better understand their behavior. That concludes the series on Monte Carlo simulation and modeling. I hope you found it useful and, more importantly, you will find it to be useful in your future. Thanks for watching and all the best for your final tasks.